Okay, in this video, we're trying to imagine the heat loss through the sidewall of a pipe, and I've got some visual aids here. Um, what made me think about this problem was I was imagining, maybe you've seen this, kind of looks like a fun noodle, right? But it's just a pipe insulator. You can stick a pipe inside here, and then, let's see if you can see it there. Whatever, there's a hole in the pipe. Yeah, you can't really see it very well, but there's a hole here. So the idea is you'd slide the pipe in here, and this has some inner radius and outer radius, so you can kind of see it. And for this aspect ratio, we're told that, or for this problem, we're told the inner diameter is D. And the outer diameter is 2D. So a lot of times on test questions, I will, instead of saying like D1 and D2, I'll make the inner and outer diameters be multiples of each other just so you get nice numbers. And you'll see in the end of the solution. All right, so this is my attempt to draw this picture. Here's a side view of that. Here's an end view. And then we're trying to think about heat conduction. What equation should you write down? 1, 2, 3. We know power equals Q over T. I'll say dQ over dt in this case is equal to K A delta T over delta X. And then in this case, I'm actually going to start, we're looking for the rate of energy transfer. Think about that. That's energy rate. That's joules per second. That has units of what? Of what? We're looking for the power. So I don't need this term anyway. So let's go ahead and write it like this. Now here comes a challenge. We're talking about heat conducting through the side wall of the pipe. If we're going to try and understand this, we need to know what the areas and lengths are and what the T's are so we can try and figure this out. So think for a second, what does the cross-sectional area look like? And think, the heat is going through the side wall of the pipe. I'm going to do it in 3, 2, 1. This is what it looks like. It's a little cylinder, or in the end view, it's kind of looking like this. The energy is being transferred through the sidewall. You can kind of see it better in the end view. The energy is going out this direction. What's a good name for that direction? Radially outwards. Okay, so the heat is transferring. So you can imagine there's hot water here and there's room temperature air here or something like that. That's causing the temperature gradient, right? And so, right, how much energy are we losing into the room through this insulation or through this pipe? All right, so what is the cross-sectional area? The area is equal to the area of the side wall of the cylinder. Is that the same at every location? No. Imagine you have your pipe. Here's the pipe. You've got some inner radius and outer radius. And the idea is you can build up that pipe out of a bunch of smaller pipes, right? And so as you go out, first the heat has to travel through this cross-sectional area, the surface area of this pipe, then through this one, then through this one, and then through this one. And so the area keeps growing as the energy goes towards the outside. That means it should get easier and easier for the energy to flow, right? Because the cross-sectional area is increasing as you go outwards. That area is 2 pi r times the height, where this dimension here, I'm calling the height. I guess you could call it the length L if you wanted to, whatever. So now, how could I figure out that this is the area? I like to think about it like this. Give me a second. Imagine you take a piece of paper and you have it as a cylinder, right? Okay, it looks like this. Here's a cylinder. Okay, sorry, you can see it there. And so now the distance here is 2 pi r. This is the height. That's the height. This distance is 2 pi r. If you just unravel it, this dimension would be 2 pi r. This dimension would be the height or the length. And so that's how I came up with this right here. Now, think about this. As you go further and further out, the temperature difference across each little subpipe, right? Remember, the temperature difference is not going to be the same from the inner to the outer, to the inner to the outer, to the inner to the outer, right? As we go outwards, they expect to have different DTs. So, and here, delta X is not really a good name for it. The heat is flowing this direction. It's going out, radially out. So notice, I would call the thickness of this pipe dr. And so I would rewrite this equation as K times area times dt dr, right? And then in this case, we say this is K, the area is 2 pi RH times dt dr, and that's equal to the power. Now in this problem, what else are we given? I'm going to read the problem again. We do know the temperatures. So in this case, we're told that this is some temperature T1 and out here is some temperature T2. So maybe we know the temperature of the hot water and the room temperature like I was mentioning. So in this case, we do not know DT, but we do know the limits on DT. What would you do? 3, 2, 1. Set up an integral, separate, and you can integrate here. So in this case, I'm going to get all the r's on one side and all the t's on the other. So maybe in this case, let's rearrange this so you get dr over r, moving this to that side, is equal to, what do you get here? We could put k 2 pi h over the power times dt. Now I'm going to check and make sure I didn't screw this up. Let's see, power comes over here, so you get k 2 pi h, you're over the power, and then we've got a dt. Now I'm moving these to the other side and they flip upside down, so that looks right. So what would you do at this point? Integrate. What do you get on this term? Log of the radius. And then we can also just stick in the limits. This is from diameter over 2 to 2d over 2. So then that would be d over 2 on this side when you do the integral. On this side, what do you get? H over power k 2 pi, and then this is from T1 to T2, right? So we're assuming T1 was warmer than there, so that would be T1 minus T2, right? So in this case, notice we get a logarithm here. And then I should reread. What are we trying to find? The rate of energy transfer per unit height. So I'm looking for power over h. So you're solving for this. So out of all that, what do I get? Power over h is equal to 2 pi k delta t over logarithm of 2 natural. Now in this case, since we're in an engineering class, look at all these numerical constants, 2 pi log 2. This would make sense to punch those in, and so you would get power over h is equal to, not approximately equal to 9.06. Is that what I found? times K delta T. So where did this log 2 come from? Right in here. It's from the aspect ratio. So if you had a different pipe with, say, basically you could get log 3 if one of the radii was 3 times bigger or something like that. So just be aware of that. And if you don't know how to do this, check the solutions that's in there. This is page 73, volume 3. If you want to read more about this one, that's enough on that.